Hello students, welcome you all to next session regarding discussion of steam turbines continued part. In the last session we have discussed regarding the problems on steam turbines for a single stage case. We have discussed a condition for maximum blade efficiency of a multi-stage turbine. In today's session we will be discussing regarding the problems for a multi-stage turbine where a steam expansion takes place in more than one stages. So we'll be learning in this particular session regarding the construction of velocity triangles for a multi-stage impulse turbine and calculating the parameters such as the power developed, axial thrust, blade efficiency for a multi-stage turbine. So if you have any queries, you can send me an email to the emails which are visible on your screen, as well as you can send me a WhatsApp message to this WhatsApp number which is available on the screen. So let us begin with the today's session regarding some of the discussion of the problems on a multi-stage impulse turbine. So the question which is available on the screen, you can see that following data refers to a velocity compounded impulse steam turbine having two rows of moving blades and a fixed row between them. Velocity of steam leaving the nozzle is 1200 meters per second. Nozzle angle is 20 degrees. Blade speed is 250 meters per second. Blade angles of first moving row are equiangular. Blade outlet angle of a fixed blade is 25 degrees. Then he says the blade outlet angle of the second moving row is 30 degrees. Friction factor for all rows is 0.9. Draw the velocity diagrams for a suitable scale and calculate the power developed, axial thrust, diagram efficiency for a steam flow rate of 5000 kg per hour. So first analyze the data given in the question, extract the given data carefully. They always remember in the question, if the term comes velocity compounded impulse steam turbine, it means it is a case of an multi-stage turbine. So if the word comes velocity compounded, which means it is a case of an multi-stage impulse turbine. Now, he says in this multi-stage impulse turbine, the expansion of the steam in this particular problem, it takes place in two stages having two rows of moving blades and a fixed row between them. So he has said that there are two rows of moving blades and there's a fixed row between them. And now from here he says the velocity of steam leaving the nozzle is 1200 meters per second, which means for the first stage it is, with respect to the first stage, velocity of steam leaving the nozzle is 1200 meters per second. Nozzle angle is 20 degrees. Blade speed is 250 meters per second, 250 meters per second. And it says blade angles of first moving row are equiangular. So with respect to the first stage, these are the given conditions. Velocity of steam leaving the nozzle is 1200 meters per second, which means V1 is equal to 1200 meters per second. Then nozzle angle he has given alpha 1, it is equal to 20 degrees. Then he says blade speed, that is U is equal to 250 meters per second. Then we have blade angles of first moving row are equiangular, which means beta 1 is equal to beta 2. These are with respect to the first stage. So the conditions which I have highlighted in the green color, they are with respect to the first stage. When the blade moves towards the second stage, when the steam moves towards the second stage, for the second stage, the conditions are given below here. That is, blade outlet angle of the fixed blade is 25 degrees. So fixed blade is a thing, but it is a thing, but with respect to the first stage outlet becomes the second stage inlet, which means it becomes alpha 3. Alpha 3 is equal to, it is 25 degrees. Then he says blade outlet angle of second moving row. Please read it carefully. Moving row blade is the thing, but it is beta. And he says it is the blade outlet angle of the second moving row. So outlet means the second stage, the outlet angle becomes beta 4. So beta 4, he has given its value as how much? It is 30 degree. It is 30 degree. Then he says friction factor. This is very, very important point, students. Friction factor for all the rows is 0.9. That is CB value. CB value is 0.9. So this blade coefficient, when we come from the first stage, we can write this as VR2 by VR1. It is 1 ratio for the first stage blades. Then from the first stage to second stage, passing through the moving and fixed blades, we write it as V3 by V2. And whereas for the second stage, we write it as VR4 by VR3. We write it as VR4 by VR3. The blade coefficient. So this value of blade coefficient for all these stages, for all these ratios, it remains the same itself, that is 0.9. He has asked us to find out the velocity diagrams. They should be drawn using a suitable scale. Calculate the power developed, that is power P, you have to calculate once you draw the diagrams. Then you have to find out the axial thrust, that is FA. And the diagram efficiency for a steam flow rate, that is the diagram efficiency thing, what it is a blade efficiency, which you need to calculate. Having a steam flow rate of 5000 kg per hour, that is MW is equal to 5000 kg per hour. This is the steam flow rate which he has assessed. With these conditions, you need to sketch the velocity triangles for a given problem and find out these parameters, that is power, axial thrust, blade efficiency for the given conditions. Now, another very important problem in this case is, always do remember that on a particular shaft, just I am drawing a stage here, please observe here. See, just I am drawing here, this is a shaft, students, this is a shaft. On this shaft, say, here I have fixed the moving blades. These are the moving blades, okay. Then behind this I have some fixed blades. These I am having some fixed blades which are fixed to the casing. So this is my casing part. Then beyond this, again I am having a next set of moving blades. And again behind this I have again fixed blades fixed to the casing. So when the steam expansion takes place in more than one stages, we call it as a multi-stage case. But students, do remember that whatever the steam expansion takes place, the expansion happens on the same shaft itself. So now together these two, so if I take together these two, that is one set of moving blades and fixed blades, I call it as one stage, okay. Then the another set, if you observe here, this is the another set together. I say this is nothing but from the first stage, it comes here together, first and second stage. This is the second stage. So both together we call it as a two-stage turbine. So now what I would like to tell you is, any number of stages the expansion happens, it happens on this same shaft itself. It has to happen on the same shaft itself, which means for any number of stages, your axial speed, that is u, it is the same. It remains the same for all the stages, which means the tangential speed for any number of stages in a multi-stage impulse turbine, it remains the same itself. This is a very, very important point. Now, let us note down the given data as I have discussed just now. That is, we are having V1 is equal to 1200 meters per second, U is equal to 250 meters per second, alpha 1, that is the nozzle angle 20 degrees. Blades are equiangular only in the first row he has said, which means beta 1 is equal to beta 2. Then for the second row he has said alpha 3 is 25 degrees, beta 4 is 30 degrees. Now, the things which we need to find out is the mass flow rate. He has given in kg per hour. We convert it into kg per second, 1.389, we get it. The blade coefficients we have noted down here, students. Then we need to find out power, axial thrust, diagram, efficiency. And the scale which we need to choose here is 1 centimeter is equal to 100 meters per second. Why? The reason is, if you observe the value of V1, it is 1200 meters per second. So when you choose scale 1 centimeter is equal to 100 meters per second, the value of V1, how much it becomes? It becomes 12 centimeter. So to draw this particular length in your answer sheet, it is a large size itself, again the 12 centimeter itself. That is the reason that I was chosen the scale as 1 centimeter is equal to 100 meters per second. Always do remember, if the velocity v1, if it is more than 700 meters per second, you have to choose 1 centimeter is equal to 100 meters per second itself. Means you will get correct answers and the velocity triangles will fit easily in your answer sheets. Now, to begin with the solution of this particular problem, I said that we have taken scale 1 centimeter is equal to 100 meters per second. And initially, I will start with the solution with the help of drawing the tangential speed, that is u. So, as I said, first, I will complete the first stage and then I will move towards the second stage. So, initially, what I will do is I will draw tangential speed. So tangential speed u is equal to 250 meters per second. So you can see here, I have drawn this one, u is equal to 250 meters per second. Say this is tangential speed u. 250 meters per second in the scale becomes 2.5 centimeter according to this particular scale. Now, what I will do is, students, please do observe here. I have V1 1200 meters per second, alpha 1 is 20 degrees. So from this side, I will place my protractor here and mark 20 degree, and I mark 20 degree. So somewhere this is the line. I mark here 20 degrees, that is alpha 1. And with a scale of 1200 meters per second, that is 12 centimeter, it cuts somewhere here it cuts. So now I will join the other side of this U to this one, and this is V1 and this becomes VR1. Measure the length of this VR1, students. Measure the length of this VR1. Also the angle of this VR1. So what I will do is I will extend this tangential speed to the other side using dotted lines, or you can use the straight lines also. Similarly, the vertical lines I draw here. This angle which I am getting here after measuring using a protractor, I will get the angle of beta 1. You have to measure this angle beta 1, students, because we have said in the question that beta 1 and beta 2 are equiangular for the first set. This is the first stage. Now, this is my VF1. Measure the length of VF1. Then from this end to the other end, that is up till here, whatever the length I get, it is nothing but it is VU1. You have to measure even this length also. So whatever the dimensions they are there with their angles, you need to do their measurements. So once I complete this VR1 beta 1, I need to shift to the other side. So what I will do is I will place the protractor here. Already we have saved that beta 1 is equal to beta 2. So beta 1 angle I have measured, and I will mark beta 2 as the same of beta 1 to the other side. So somewhere here I get this is beta 2. What about the length? You have to make use of this particular relation, students, that is CV is equal to VR2 by VR1. Just now we have measured the length of VR1. We know the value of CB. If you substitute, you'll get the value of VR2. On this particular line, cut the value of VR2. It cuts somewhere here. This is the length of VR2. So wherever it cuts, this is the length of VR2. Join from that particular point, you will get the value of V2. And this extend this to the other side here on the same side, both vertical and horizontal lines. This is VF2, and here this particular angle, it is alpha 2. From here to here I get it as VU2. Students, please observe here carefully. For this case, especially for this case, now from this particular point, that is from here to here, whatever the length is there, we say this as delta VU1, delta VU for the first stage, Roman number 1, first stage, which is nothing but it is a sum of VU1 plus VU2. Similarly, this height, that is from this particular end point, that is from here to here, we mark this as delta VF for the first stage, Roman 1, VF1, that is delta VF for the first stage. I write it as VF1 minus VF2. So all the things we have measured, all the things we have completed with respect to the first stage. Now what I will do is I will move towards the second stage. To move to the second stage, I said that the tangential speed, it remains the same. So what I will do is I will draw some projection lines downwards. You can see here, I am drawing the projection line downwards. And somewhere here, I will draw this line, my tangential speed u. Okay. So a little bit top, I will take it this one. So what I will do is somewhere here, I will draw u. Okay. So this is the same tangential speed. So again, once more, I am repeating, any number of blades are mounted on that particular shaft. The shaft speed remains the same, but the tangential speed. That is the reason that the u also for the second stage, it remains the same. Now, as I have said, we will begin with the second stage construction. So already in the question, he has given us the value of alpha 3 is equal to 25 degrees. So what I will do is I will place my protractor here and mark 25 degrees. So somewhere here it comes. This is alpha 3. What about the length? To find out this length, now what I will do is I will make use of this particular expression, students, that is CB, and this one, that is V3 by V2. I will make use of this one. CB is equal to V3 by V2. So V2 length we have measured. We know the value of CB. So I will get the value of V3. So once I get the value of V3 from this particular equation, that is CB is equal to V3 by V2, using this relation, I will get the value of V3, and the length of that V3 I will cut on this particular line. So wherever it cuts, from that you join to the other part of the tangential speed. This is V3, alpha 3. Similarly, this is, I get it as VR3. Measure the angle, students, by drawing these extension lines on both sides. This becomes beta 3. And this vertical height, it is VF3 with this value of VU3. I hope the half part of the second stage is completed. Measure the values of VF3, measure the values of VU3 also. Now, for the second stage, he has not said that the blades are equiangular, but instead of that, he has given the condition for us is, students. He has said clearly that the outlet moving blade angle, it is this one, beta 4 is equal to 30 degree. He has given. So what I will do is I will place my protractor here, students, and from here 40 degree I mark to the other side. So this is my beta 4. Now the length. Now here, to find the length, what I will do is, students, I will take help of the blade coefficient, that is this particular equation, that is CB is equal to this one, that is VR4 by VR3. I take this particular expression, that is CB is equal to VR4 by VR3. I take the help of this particular equation and I will get the value of VR4. So whatever the value of get of VR4, I cut it on this particular line and I join to the other side. It is here. So this becomes VR4. This becomes V4. Then extend these lines on the both sides. That is here. You can see this angle is alpha 4. Then this vertical height, this one, this is VF4. Then measure this one, this is VU4. So as we have done for the first stage, students, as we have done for the first stage, here also for the second stage, students, that is, just I will write down the equations here. For the second stage also, students, what we will do here is delta VU for the second stage. We write it as VU3 plus VU4. So whatever the values you have measured, you need to sum up them. You will get the value of VU3 plus VU4. Similarly, delta VF for the second stage, it is VF3 minus VF4. These are the things you need to find out. So if you find out these things, only the thing is next you have to substitute the values in the equations and get the answers. So let us see. Already I have completed this problem and I have got the sketch in this fashion, students. This is my sketch. So you can see here, I have done this construction of this particular problem. If you observe here, the tangential speed, I have taken down the lines and I have taken the same speed. As I said, all these blades are mounted on the same shaft. That is the reason that they rotate at the same tangential speed u. Okay. So you can see here, once again, I will show here these points from here to here. That is from this end to this end, whatever I am measuring, this is delta VU for the first stage. Similarly, at the bottom, from here to here, this is delta VU for the second stage. You can measure it. At the same fashion, even for here also, that is this height from here to here, this becomes delta VF for the second stage, that is VF3 minus VF4. The same even for the upper one also, that is VF1 minus VF2. Okay. So on measuring these particular values from the graphs, I have got these results. I have got for the net velocity triangle for the first stage, VR1 is equal to 980 meters per second. Beta 1 is equal to beta 2 is equal to 25 degrees, which was given in the question. VF1 is equal to 410 meters per second. Beta 1 is equal to beta 2. I have got it as 20 degrees, 25 degrees, measured value. VU1 is 1130 meters per second. U value is 250 meters per second. Then for the outer velocity triangle, students, I have got these values. V2 is equal to 60 to 660 meters per second. Make this correction here, students. It should be 25 degrees. It is a misprint. Beta 1 is equal to beta 2 is equal to 25 degrees. Then using the blade coefficient equation, CB VR2 by VR1 is equal to 0.9. I got the value. These are the following values. That is measured value. VR2 is 882 meters per second. VF2 374 meters per second. VU2 545 meters per second. Alpha 2 I have got it as 33.5 degrees. So once we construct the first row set of velocity triangle, then entirely what I do is I represent the delta VU for the first stage. V1 plus VU2 is equal to 1675 meters per second. Similarly, delta VF for the first stage as 36 meters per second. Now the same what I have done is I have measured the values for the second row also. So for the second row, I have got alpha 3 is equal to 25 degrees. Then I have got CB is equal to, using this particular value, I have got the value of V3 as 594 meters per second, VR3 as 400 meters per second, beta 3 as 41 degrees, VF3 as 270 meters per second, then VU3 as 530 meters per second, U 250 meters per second. Then for outer velocity triangle, we have V4 200 meters per second, CB 0.9. Using that, we have got the value of VR4 as 360 meters per second, VF4 185, VU4 80 meters per second. Delta VU for the second stage, VU3 plus VU4 I got it as 610, whereas delta VF for the second stage, VF3 minus VF4 I have got 85 meters per second. So once we have found out all those things, you need to substitute those values in the equation. That is, power developed P is equal to M dot E. So now here E, that is our Euler's equation. We have to write with respect to both stages, that is summation of both. So I write it as M dot U into delta VU for the first stage plus delta VU for the second stage. And I get the answer as 793.446 kilowatt. Similarly, axial thrust FA is equal to M dot by GC. So axial, we have to take the axial force for both the stages. That is Vf1 for the first stage, for delta Vf for the second stage, and I get the answer as 168.069 newtons. And the last, that is the blade efficiency, students. Here, the blade efficiency, it becomes 2u delta vu, because here the two stages, I write it as delta vu for the first stage plus delta vu for the second stage, summation of both by v1 square, and I get the answer as 79.34 percentage. Hope this thing is clear to you. Now, moving ahead. Similarly, we have another problem, second problem. Here he says, the velocity of steam at the exit of a nozzle is 440 meters per second, which is compounded in an impulse turbine by passing successively through moving, fixed, and finally through second ring of moving blades. Tip angles of moving blades throughout the turbine are 30 degree. Assume a loss of 10%. He says 10% loss in velocity due to friction when steam passes over the blade ring. Find the velocity of moving blades in order to have a final discharge of a steam as axial. Also determine the diagram efficiency. So it's a homework to you, students. You can try at your home this particular problem. Just I will give you the hints. So if you observe the question carefully, he has said that the velocity of steam at the exit of the nozzle is 440 meters per second. That is, he has given the value of exit of the nozzle, that is alpha 1. He has, the speed he has given, that is V1. He has given its value is 440 meters per second. Then he says it is compounded in an impulse turbine passing successively through all moving, fixed, and finally through second ring of moving blades, which means there are two sets of blades, two-stage turbine it is. Then he says tip angles of the moving blades. So tip angles of the moving blades in the sense the angles, that is beta 1, beta 2, they are all equal to 30 degrees. So beta 1 is equal to beta 2 is equal to beta 3 is equal to beta 4 is equal to 30 degrees. Then another point, it says there is a loss of 10% in the velocity due to friction. So that is the blade coefficient. So if there is 10% loss, what does it mean? Our blade coefficient, after losing 10% loss, it is having the value of CB is equal to 0.9. And this CB is equal to 0.9. I can write this as for all the blades he has said, which means first V2 by, VR2 by VR1. Then we have V3 by V2. And finally, we are having VR4 by VR3, which means this blade coefficient loss is same for all the blades. You need to find out the velocity of the moving blades in order to have a final discharge. Please note on this point, students. He says the final discharge of the steam is axial. So the final discharge of the steam is a thing, but he is representing the outlet velocity of the second stage. And he says this final stage is axial in nature, which means the final stage, that is V4, that is the final discharge, it is axial in nature, which means V4 is equal to VF4. This is an important point. These are the given conditions in this particular problem, students. These are the given conditions in this particular problem. So just I will give you some points and I will help you out here. As I said, these are the given conditions. To begin with the solution of this particular problem, so whenever I want to begin a solution, you need to have a tangential speed. And once you have tangential speed, that is you need to you assume a particular scale. So if you have a particular value of u given in the question, you can assume the scale. But here for us, the u value is unknown. But instead of that, we are having v1, even we are having beta 1. So even for us, the alpha 1 is also missing, which means the beginning of the solution is very much critical here. We know the condition for a given problem that it is two-stage problem. So now what we can do here, students, is we need to begin the solution of this particular problem starting from the bottom towards the top, that is starting from second stage, we need to move towards the first stage. So how it can be done? Please observe here. Just I will show you here the things. We don't know the scale. So what I will do is just I'll assume sum of scale as u value. So what I will do is I am assuming my u value as, that is, assume u is equal to 3 centimeter. I have assumed. Why I assumed? Because already we know, if we have solved many number of problems, we have seen the value of u not more than 5 centimeters. So what I will do is, as it is a multi-stage turbine, I will try to assume the u value is 3 centimeter. Don't go beyond the value of 3 centimeter also, because if we extend the value of u as 5 or 6 centimeter, then the scale, that is the diagram, it becomes larger. Or else if you take the value of u as smaller than 3, that is 2.42, again the scale becomes very much smaller, the size becomes smaller. So your answers won't be accurate. So you can take it around as u is equal to 3 centimeter. So as I said, in this particular problem, the solution begins from the bottom, that is from the second stage. So with u is equal to 3 centimeter, first I will draw this one. Then to begin, we need alpha 3 or alpha 4, which are not available to us. But instead of that, he has given beta 3 and beta 4. So what I will do is, students, please observe here. Beta 4 is equal to 30 degrees and beta 3 is equal to 30 degrees. I draw it on both sides. First, beginning with beta 4. Beta 4, I am drawing here. You can observe. But I don't know the length of VR4. But another thing, what I am given in the question is, he has given another condition, that is V4 is equal to VF4. Axial velocity is, the final discharge is axial in nature, that is V4 is equal to VF4. What I can do is, from the other side here, I will draw a vertical line. Wherever it cuts this one, this becomes my V4 line. So I have drawn a vertical line, and wherever it cuts, that is at this particular point, this is nothing but the length of this one V4, that is V4 is equal to VF4. And this particular length is what now? It is VR4. Measure the values of VR4, V4, VF4. And in this case, here VU4, that is VU4 is equal to 0. Why? Because V4 is equal to VF4. Now what I will do here is, once I have measured the values of VR4, using this relation, students, VR4 by VR3 is equal to CB. What I will do is, I have the value of beta 3. So I will draw the value of beta 3 to the other side, that is the value is 30 degrees. Somewhere here I will draw it. I have the value of VR4 by VR3 from this equation. I will cut somewhere here the value of this particular line, that is VR3, and I will join to the other end to get the value of alpha 3. This is my length P3. So say extend it to the other side to complete. This is VF3, and this is from here to here entirely, it is VU3. Measure all these values. So you can see here we have completed the bottom velocity triangle. This is beta 3. Now moving to the upper side. So extend these lines, draw the projections of the tangential speed. So somewhere here I will draw this tangential speed U. And moving from the other side, what I'm having the value of beta 2. So what I will do here, students, is I will start with this point, that is from here. I will mark beta 2 is equal to 30 degrees, that is here. Beta 2 I get. But again, I don't know the length of VR2. But what I can do here, students, now is, with the help of the blade coefficient equation, that is here, I have this particular point, that is V3 by V2 is equal to 0.9. Just now I have got the value of V3. What I will do is, I will get the value of V2, and from this end I will place here the value of V2, whatever I get from this particular equation, V2 value, I will get some answer. Whatever the answer I get from here, that particular scale value, I try to cut wherever it meets on this particular line. So wherever it meets, if this point is here, and I will join it. This becomes the length of V2, and this is the length of VR2. Measure both the values. V2 value we have got from this equation. Now measure the value of VR2. Similarly, extend to the other side. Measure the value of alpha 2. This is the value of VF2. This is the value of VU2 up till here. Hope this thing is clear to you. Now coming on to the last part. Once I have got this thing, I need to go for beta 1. So what I will do is from here, I keep my protractor and mark beta 1 as 30 degrees. Somewhere here I get. I have got the value of VR2. Now what I will do is I will make the use of this particular relation CV is equal to VR2 by VR1. And somewhere here the value of VR1 I can cut on this particular scale. Now what I will do is I will join this one to the other side where I will get the value of V1. Making an angle alpha 1. Measure both these values V1 alpha 1. Similarly extend this line. This is VR1 making an angle beta 1. Then this is VF1 and this is PU1 up till here. So now you need to find out even these two conditions. That is, please note here, you need to find out delta VU for the first stage, which is equal to VU1 plus VU2. Similarly, you need to find out delta VU for the second stage, delta VU for the second stage, that is VU3 plus VU4. And another point is you need to find out even delta VF for the first and second stage, that is, I'll write here delta VF for the first stage is equal to VF1 minus VF2. Similarly, delta VF for the second stage, that is VF3 minus VF4. This you need to find out. You have to measure all these values. Please note here, students, whatever the values you have got here for all, you have got in terms of only centimeters per second. That is, you have got the value of V3, VR3, whatever the velocity terms you have measured, that is VF for all the velocity terms. You have got those values in only centimeters, not in a meter per second. Why? Because still we don't know. But once you complete your velocity triangle and you measure the value of V1, you get the V1 value as some centimeters, say around some 20 centimeters, some value you get. Now what you should do is you should divide this 440 divided by 20. Just I am saying this is not the exact answer. I am assuming just we have got some around this value. Whatever the answer now you get, now this is your actual scale, that is 1 centimeter is equal to the corresponding answer whatever you get here. Then what you should do is whatever the measured values in centimeters are there, you have to convert them into respective meters per second. That is, now I have completed the problem here. Just I will help you. This is my sketch. These are the values. You can see here I have got all the values in centimeters itself. You can see here these are the corresponding values. See, for the second row we have got these values, inlet as well as outlet velocities. Similarly, for first outlet velocity triangle, these are the values we have got all in centimeter itself. Inlet velocity triangle we have got in centimeters. So once you have got in centimeters, as I said, after completion of velocity triangle, V1 value is 440 meters per second, and my measured value through the scale is 13.3. I will divide 440 by 13.3, and I get the value as 33.08 meters per second, which means now the scale is 1 centimeter is equal to 33.08 meters per second. Everywhere make the conversions by multiplying with this factor 33.08 meters per second. See, you can see here I got the value of U, delta VO for the first stage, VO for the second stage. Similarly, blade efficiency, that is VO for the first stage plus VO for the second stage, is equal to divided by V1 square, and I get the answer as 80.375 percentage. Then these are the things which they have asked in this particular question. I hope these things are clear to you. If you have any doubts, you can send me an email or send me a WhatsApp message also. So in the next class, we'll be discussing some more parts with respect to the hydraulic turbines and the other applications. Okay, we shall stop here, students. Thank you.